In this video, we solve problem 9 of Unit 12. In it, we are given a set of capacitors, and we're asked to find the charge on each capacitor. For doing this, given that the upper branch shows two capacitors in series and the lower branch is showing also two capacitors in series, the best would be to find the equivalent capacity of the sets in the upper branch and the set in the lower branch. Because once we've done this, we know that the difference of potential between the plates of these equivalent capacitors in the upper and lower branch is going to be the same, and it's going to be the one between points A and V, which is directly given in the problem, which is 12 volts. It's what we normally call V. So from this set to we're going to focus on the upper part, and we're going to look for the equivalent capacity. So we want to go to something that looks like this. This is point A. This is the equivalent capacity of the upper branch. This is the equivalent capacity of the lower branch, and this is point B. If we want, we can call this capacitor A, and this is going to be capacitor B, okay? So as the upper branches, the capacitors are in series, we know that the capacity, the equivalent capacitance is going to be the inverse of 1 over C1 plus 1 over C3, which is equal to 1 over 1 microfarad plus 1 over 3 microfarad to the minus 1. So if you do the numbers here, you can find that this is 3 over 4 microfarads. And the same for capacitor for the equivalent B, which is 1 over C2 plus 1 over C4 to the minus 1, which is 1 over 2 microfarads plus 1 over 4 microfarads to the minus 1, which is 4 over 3 microfarads. Once we know this equivalent capacity, we can quite easily calculate the charge, because we know that VA is going to be equal to VB, which is equal to the potential difference between point A and point B, because these lines mean the wires, and all the wires have the same potential. So all the points here have exactly the same potential, while all the points here have the same potential, which is potential B, okay? So this is 12 volts, and we also know from the definition of capacitance, this is the ratio between the charge held by a capacitor and the potential difference across plates. So from here we know that the charge held by a capacitor is going to be the capacitance times the potential difference. So for charge of capacitor A, this is going to be CA, which we've already calculated, times this V. This is 3 over 4 microfarads times 12 volts. This gives you 9 microcoulomb. And charge in B is equal to the capacitance in B times the potential drop across the plates, which is 4 over 3 microfarad times 12 volts, which is 16 microcoulomb, sorry. And as capacitors 1 and 3 are both set in series, and its equivalent capacitor is capacitor A, this means that this charge in A is the same charge as the one in capacitor 1 and the one in capacitor 3. And on the other hand, the same we can get the same from the lower branch. This has to be equal to the charge in 2 and equal to the charge in capacitor 4. So we already have solved for the first question. The second one was to find the total energy stored in the combination. This is quite easy. There are several ways to do it. The simplest way with what we already know is finding the energy stored in capacitor A, the energy stored in capacitor B, and then adding them up together. So we can do this. So in B, we're going to look for the energy stored in capacitor A, which is 1/2 times the charge in A times the potential drop across. So this is 1/2 times 9 microcoulomb times 12 volts, and the same for B, 1/2 QB V. This is 1/2 times 16 microcoulomb times 12 volts, and if we add everything together, A plus B, this is going to give you 0.150 millijoule. Okay, I leave to you to see that that you can obtain the same by calculating the energy stored in each capacitor separately and adding everything together. And also you can end up with the same number if you calculate which is the equivalent capacity of the set and calculate there the energy stored. In the last part, we are asked to calculate the energy stored in the case that we use a dielectric of dielectric constant kappa equal to, and this dielectric is introduced between the plates of each capacitor. So if this dielectric is introduced for each inside each capacitor, then the new capacitance is going to be the old one times this kappa, and this happens for the 4 of them, because the 4 of them have had introduced this dielectric. Okay. So if you redo the numbers, you will end up showing that the equivalent capacity of A in this new set is going to be the old one, which we already have there, times kappa, and for B it's going to be the old one times kappa. So once we know this capacitance, then we can easily calculate the new capacitance of the set. If you want, we can think of going from the new CA and CB to just the equivalent one, which is the combination of capacitors A and B that were in parallel. So if we do this, the equivalent capacity is going to be the addition CA prime plus CB prime, and this provides you with, if you do the numbers, 50/12 microfarads. In this case, you can calculate the new energy stored, which is going to be 1/2 of this equivalent capacity times V, which provides you with 0.300 microjoules. Okay, this is just double the original energy stored.